Okay, so today I'm going to prove the sum of the reciprocal of squares is equal to pi squared over 6 using a different method than usual. I'm going to use these two non-elementary integrals right up here. And this should be the integral from 0 to pi over 2. And the reason these integrals are non-elementary is because of this n. We can't integrate cos 2n of x. We need to know if we're integrating cos squared, cos cubed, cos the fourth of x, etc. So for this proof, all steps will be to assume that n is greater than or equal to 1. These integrals they kind of break down before n is equal to 1. Okay, so we're going to start with a sub n, this first integral here, and we're going to mess around with it a little bit to find some interesting properties about it. So I'm going to integrate by parts a sub n, and I'm going to do that by setting it equal to the integral from 0 to pi over 2 of the cos 2n minus 1 of x multiplied by the cosine of 1 of x, or just the cosine of x dx. Now with this, we can integrate the cosine of x and differentiate the cos 2n minus 1 of x if we use integration by parts. So that is going to be equal to the integral of cosine of x, which will be the sine of x, multiplied by the original, or the cos 2n minus 1 of x, and we'll evaluate that from 0 to pi over 2. Then we will subtract the integral from 0 to pi over 2 of the derivative of the cos 2n minus 1 of x, which is going to be negative 2n minus 1 times the sine of x times cos 2n minus 2 of x. And all of that will be multiplied by the integral of cosine of x, which again is the sine of x. So I will make the sine of x here sine squared of x dx. Okay, now this is actually going to zero out because the cosine of pi over 2 is 0 and the sine of 0 is 0. So we will cross this out. I will factor this negative out. So we actually have the positive integral from 0 to pi over 2. And we can factor out the 2n minus 1 as well. So why don't I do that? We'll have 2n minus 1 in brackets times the integral from 0 to pi over 2. And I'll write sine squared of x as 1 minus the cosine squared of x times cosine 2n minus 2 of x dx. Cool. Now this is very good because we can distribute this 2n minus 1 and separate this into two integrals. So we'll have the integral from 0 to pi over 2 of the cos 2n minus 2 of x minus 2n minus 1 times the integral from 0 to pi over 2 of cos squared of x multiplied by cos 2n minus 2 of x, which will just be cos 2n of x. So this will actually be equal to 2n minus 1 times a sub n minus 1 because of that cos 2n minus 2. And then that will be subtracted by 2n minus 1 again, multiplied by just a sub n. And this is a really interesting property of our a sub n, that a sub n is equal to 2n minus 1 times a sub n minus 1 minus a sub n. So I'm going to move this over to the other side. So we will have a sub n, and I'll factor that out from 1 plus 2n minus 1, which will be equal to 2n minus 1 a sub n, or a sub n minus 1. Now this will be just 2n, and then we can use that to prove that n times a sub n. So we have 2n a sub n is equal to 2n minus 1 a sub n minus 1. We can use that to prove that n a sub n is equal to 2n minus 1 over 2 a sub n minus 1. And that will be our first interesting property of a sub n that we will use to prove the reciprocal of squares. Okay. Now the second one, we will integrate by parts a sub n again. But we will use 1 times the cosine 2n of x. So our a sub n will be equal to the integral from 0 to pi over 2 of 1 times the cosine 2n of x dx. Now we can integrate 1 and we can differentiate the cos 2n of x. So if we do that, we will have the integral of 1, which is just x, times the cosine 2n of x, evaluated from 0 to pi over 2, which will again zero out. Then we will subtract the integral from 0 to pi over 2 of the integral of 1, which is x, times the derivative of cosine 2n of x, which will be negative 2n times the sine of x times cos 2n minus 1 of x dx. Now this will zero out. If we take the negative out, we will be left with the positive integral from 0 to pi over 2. And we can take the 2n out as well, so I'll put that out there. Of the sine of x times the cosine 2n minus 1 of x dx. And if I divide the 2n on both sides, we will have a sub n over 2n is equal to this integral here. Now we will do integration by parts again, so that we can relate this integral here. Oh, and I left out the x there. So we can relate this integral to our b sub n. Okay, cool. So we have a sub n is equal to x times the sine of x times the cosine 2n minus 1 of x. So in this time we will integrate x and we will differentiate sine of x times the cosine 2n minus 1 of x. So overall we'll have a sub n over 2n, which will be equal to the integral of x, which is x squared over 2. And we'll multiply that by the original. So we'll have x squared times the sine of x times the cosine 2n minus 1 of x all over 2, evaluated from 0 to pi over 2. Now that will zero out again. So we will be left with the negative integral from 0 to pi over 2 of the integral of x, which is going to be x squared over 2. And we're going to have to multiply by this derivative here. So we're going to have to use the product rule. So this will get a little bit long here. So first we'll take the derivative of sine, which is the cosine of x, and that will be multiplied by the original function, which will actually just give us the cosine 2n of x. Just like that. Then we have to add the derivative of sine of x times the cosine 2n minus 1 of x. And that is going to give us the negative 2n minus 1. Yes, negative 2n minus 1 times the sine of x times cosine 2n minus 2 of x, and that will be multiplied by sine of x. So this will become sine squared of x, and all of that's over 2. Now we can take our half right outside of the integral, so we will have negative a half times the integral from 0 to pi over 2 of x squared times the cosine 2n of x, which is actually our b sub n. Yes. Then we can write the sine squared of x as 1 minus cosine squared of x again. So we'll have overall x squared times the cosine 2n of x minus 2n minus 1, 1 minus the cosine squared of x. And that's going to give us, if we distribute cos 2n minus 2 of x plus 2n minus 1 times the cosine 2n of x dx. Now we have cos 2n here twice, so we can simplify this further. So we have 1 cos 2n plus 2n minus 1. So that is just going to be cos, or 2n cos 2n of x. So that's going to give us the negative, and we can take the 2n outside, but first I'll simplify it first. So we have negative half times the integral from 0 to pi over 2 of x squared times 2n cos 2n of x minus 2n minus 1 cos 2n minus 2 of x dx. Like that. Now we'll take this 2n out and we'll split it into two integrals. So we will have negative 2n over 2, and I'll start a new line for this so I don't cut it off. Okay. So overall we have a sub n over 2n is equal to negative 2n over 2 times the integral from 0 to pi over 2 of x squared cos 2n of x dx, and that is our b sub n. Then we will add 2n minus 1, because we're subtracting, negative is a negative is a positive, and it's by a half, so negative 2n, or 2n minus 1 over 2 times the integral from 0 to pi over 2 of x squared cos 2n minus 2 of x. And that is going to be b sub n minus 1. Cool. So this leads us to our second property that we will need to prove the reciprocal of the squares. And that is going to be that a sub n over 2n is equal to 2n minus 1 over 2 b sub n minus 1 minus 2 cancels, n times b sub n, like this. Cool. Now we will write this in terms of a sub n over n squared, or 1 over a sub n. So a sub n will multiply by 2 over n on both sides, or 2 will multiply by 2 over n a sub n on both sides, which will be equal to 2n minus 1 over 2, which will cancel, of course, 2n a sub n b sub n minus 1 minus 2n b sub n over n a sub n. So let's cancel and clean this up here. So this is going to simplify, that's going to cancel. We're going to be left with 1 over n squared, which is what we want, and we're going to use that to find our sum. This will cancel, this will cancel. Yes. So we'll have 2n minus 1 over n a sub n, and we know what our n a sub n is equal to, times b sub n minus 1 minus 2 b sub n over a sub n, like that. Cool. Now, we will sub in our n a sub n with what we know from before. So I'm going to erase this from up here. Yes, erase this again. Yes, this is looking really good now. So 1 over n squared will be equal to 2n minus 1 times b sub n minus 1 all over n a sub n, which is equal to 2n minus 1 a sub n minus 1 over 2, like so. And then we'll subtract off 2 times b sub n. Now we can flip this, multiply, this will cancel, and we will be left with 1 over n squared is equal to 2, which I'll factor out of the whole thing, b sub n minus 1 over a sub n minus 1 minus b sub n over a sub n. And this is what we will use to prove the sum of the reciprocal of the squares. Because if we sum from k is equal to 1 to any value of n, which is what we'll do first. So we'll actually do the sum from k equals 1 to n, not infinity just yet, of 1 over k squared. That will be equal to 2 times the sum from k is equal to 1 to n of b sub k minus 1 over a sub k minus 1 minus b sub k over a sub k, like that. And now this is really nice because this is actually going to telescope. And I can show you that because if we start with 1, we'll have b sub 1 minus 1 over 0 over a sub 0 minus b sub 1 over a sub 1. And then we go into our second term, we'll have plus b sub 1 over a sub 1 minus b sub 2 over a sub 2, and so on. So all of the middle terms will cancel off and we will be left with the first and the last, and that's why it's called the telescoping sum. So this will actually be equal to 2 times b sub 0 over a sub 0 minus b sub n over a sub n. Okay, now b sub 0 over a sub 0, that's just a constant. So we can figure out what that is. So if we put in b sub 0 into here, we will have the cos. So b sub 0 should be equal to the integral from 0 to pi over 2 of x squared times the cos of x to the 0th power, which is going to be 1 dx. So the integral of x squared is going to be x cubed over 3. So we sub in that, and we'll have pi over 2 cubed times a third, which will be equal to pi cubed over 8 times 3, or 24. Pi cubed over 24. So that's b sub 0. A sub 0 will just be equal to the integral of 1, so and then we evaluate from 0, so it's just pi over 2. So now b sub 0 over a sub 0 will be pi cubed over 24 divided by pi over 2, or multiplied by 2 over pi. One of those will cancel. This will simplify to pi squared over 12. So we'll have 2 times pi squared over 12 minus 2 b sub n over a sub n. And we can simplify this to pi squared over 6. And that's what we're looking for. So we have pi squared over 6 minus 2 b sub n over a sub n. Now all we have to do is take the limit as n approaches infinity, because we have technically the sum from k is equal to 1 to n. So if we have, as n approaches infinity, b sub n, if we just look at the actual function of x squared times cos 2n of x, the area under this region here, as n approaches infinity, will get smaller and smaller. But because it's multiplied by that x squared factor, this will approach 0 as well as this, but our b sub n will approach 0 much faster than a sub n. So that means as we approach infinity, this is going to approach 0. And that means that the sum from k is equal to 1 to infinity of 1 over k squared is equal to pi squared over 6. Okay, I hope you enjoyed this definitely non-traditional proof of the sum of the reciprocal of squares. I adapted this from the Higher School Certificate Mathematics Extension 2. It was a problem on that exam. And it's definitely a really neat way of proving this pi squared over 6 phenomenon. So like the video and subscribe, and thanks for watching.